Microservices are a specific kind of service-oriented architecture, or SOA, that leverages small, stateless processing for improved scalability and resiliency. Microservices design is a popular approach to applications, and this lesson explores how microservices work and support on the Google Cloud Platform for microservices.
So let's go ahead and start here with microservices. Now, microservice architecture, it's a method of developing software applications as a suite of independently deployable small modular services. And this makes it like tiny Lego building blocks. You can you can get very good at making one small little thing run very, very well. And then, of course, if you combine those together, you can make an entire service. Now, each service is going to run as a unique process, and it communicates through a very well-defined lightweight mechanism. Think of Google Cloud PubSub, which is a message queuing service. So if you need applications to send messages or payloads to each other, that's a good method or a lightweight mechanism that can do so. Now, also, each service is going to contribute to some individual business goal. So you don't want to get too micro with microservices. So why would we ever want to do this? Well, there are a number of benefits. It's atomic, they're single-purpose code, which makes it very easy to develop and maintain. It also does one thing, and it does it very well. So troubleshooting is going to be very easy, and it's very fast at what it does. You could write the whole, an entire function, for example, say an assembly. And now normally that would be just a function that would be called within an application. Now it can actually exist as a separate service that can be called upon and actually used by other services that it may not even be intended for. I mean, think of APIs, right? It also supports A/B testing, so you can quickly swap in and out that particular component without having to recompile a big, large application and see how it functions in a production environment. It's also independently developed services. They aid in things like fault isolation, debugging, redundancy, and resiliency, because we can just make as many clones as we need to satisfy our requirements. But it's not all, what's the analogy? It's not all flowers and pumpkins. Maybe it's a fall thing. But it is harder to understand how microservices interoperate, because you're going to have all these different services which don't rely on each other, but they need some kind of mechanism to talk to each other. So unit testing is going to be easier because they're individual, but integration testing, how well do these services work together, can be a little bit difficult, because you could have a chain of events and you have to understand where the source cause is. So much like an airplane that's a little late getting into the gate, or a weather delay, if a few of them get in, it's going to affect connections coming in from different locations. The departure may not be on time. It creates this huge chain of events. But in a way, you can think of airlines very much like microservices at a very grand scale. So one little hitch in the system can also have a huge chain of events effects on that. So how does it complicate the business logic? Well, if you take a look at a simple service, you have a unified banking service. You have a machine that's going to accept deposits and one that's going to accept withdrawals, or vice versa, right? If you put money in, right, that money isn't electronically transported over to another machine so it's safe at the bank. The bank needs to be able to determine with the other side, okay, do you accept this? If you do, have you updated your side? We now have more dollars added to this account, so this way we'll deprecate it from what we see locally, and vice versa. If we're going to hand out cash, then we have to deprecate it from the user's account. And that can all happen, right? We won't give the money until we have that confirmation. Now, what happens if you have a microservices in which you actually have segregated deposits and withdrawals? Well, if you deposit money into here, right, you need to somehow be able to update with the withdrawal service so it knows, yeah, I can now give out that money that was just deposited. Say there was no balance. Well, if this microservice goes down and that communication goes down, could it be possible that somebody could actually withdraw that money without it ever being actually recorded against their account? Or they wouldn't be able to withdraw because it says, you know what, you have no money and I don't see a deposit. So understanding that communication protocol between microservices can be a little bit complicated, but fortunately we've been doing this for a long time and we have a number of mechanisms to actually monitor and help troubleshoot that. So the point here is you want to use microservices where they make sense in the design. So they make sense when there's many consumers of an atomic unit of functionality. If a lot of people are going to be doing the same thing over and over, then that makes sense. I mean, sometimes you do these one-off scripts to fix things, but this is really a core component. If people are going to be uploading images all the time and they have to be processed, well, you can make a separate process for allowing the uploads, storing the uploads, and then a separate microservice to process the uploads. So when there's one consumer of tightly coupled functionality, microservices services at overhead without much benefit. So if you could encapsulate this all into one consolidated service, you may not need to segregate that. If you remember back in the day, there was SendMail. SendMail was just this one binary that could process the queue. It could send emails, accept emails, etc. And then came along something like Postfix and QMail, in which every service was created as a small microservice, even though it resided on the same individual machine. All of these processes could literally be picked up and moved to other actual machines to handle incoming mail, outgoing mail, SMTP, spam deliveries. So these concepts have been around for a while. And if you need just one more example, if you've ever seen the movie Big Hero 6, right, the young boy there, he creates something called microbots, which is a little circle with two little legs. That's it. And you can program a microbot to communicate with all these other microbots to actually create something as a whole. It could become scaffolding, it could become a robot, it could be wheels, anything as they were joined together. And so that's a bunch of microservices using some kind of logic to actually perform a single larger, grander function. So how do we solve this? Well, Google has a number of different offerings. The number one is Cloud Functions. So this is a lightweight compute solution that we offer as a managed service. It allows developers to create these single-purpose standalone functions that respond to cloud events. So you don't have to manage the server. You don't have to manage the runtime environment. It does run JavaScript on Node.js, so it does provide the ability to do front-end and back-end functions, which is great. And Cloud Functions are fantastic for a microservice design. Again, you're solving the problem of having one specific service, whether it's a front-end or a back-end service. It can make calls to other services when it's done to kind of pass along the business logic. There are limitations. Cloud Functions is not a low latency service, right? Even though it's written in very lightweight JavaScript, it's not designed to be low latency. Whether that's on purpose or because of our infrastructure, that's just something you have to deal with. So as a managed service, that means you can't really adjust for that. If you scale, it's not like you're going to reduce the latency because you have no knobs or switches. As a managed service, you get what you get. If it doesn't work, then you find another solution which gives you more granular control over the infrastructure to reduce that potential latency, but still offer microservices. Think of Kubernetes, for example, or even Compute Engine with your own optimized and tuned environment. So let's take a look at an example service using using Cloud Functions as microservices. So here what we're going to do is we are going to be ingesting an image, and we want to actually translate what we see, the text that's in that image. So the first thing is we accept a file upload, and then we have a Cloud Function which is going to do OCR. So we're going to recognize characters inside of that. Now this function itself doesn't have that logic, so it's going to use the Cloud Vision API. It's going to pass that image in there. It's going to accept back whatever text is discovered, and then it's going to pass it on to the next function. Well, since it doesn't know what that function is, what it does is it publishes it to a topic, which means it's not responsible for the message actually getting there. It's done. It processed it, it put it back onto a queue, and now that queue is going to be pulled from another function. So we call these subscriptions. So the translator will subscribe to the topic that the OCR function has published to. The translator says, well, give me that text. All right, let's go ahead and translate that text by passing the text to our translation API. Then that will pass back the translation, and then that function will put it back on the stack, which will then publish to a new topic, which will be subscribed by the file writer. Now the file writer is going to just simply read from that topic and then output that data to Google Cloud Storage. So you can see here, the big clue is the events that are going to be occurring using some kind of mechanism. In our image storage bucket, we can actually publish notification events, which can call functions. And then of course we have Cloud PubSub, which can be our message queuing service, allowing inter-processor or inter-function communication between these different functions without them having to know about each other. So what if we wanted to do this on Google App Engine? In fact, this is where Google Cloud Platform started, was on App Engine. The benefits of App Engine: full code isolation. All you do is just simply publish your code. It can be in many different languages. All code is going to be executed through HTTP or RESTful API calls. So you already have this service built in for you. In this case, you can have multiple versions. You can have multiple services running simultaneously. And we have a number of shared services that allow them to communicate, whether it be shared Memcache, Cloud Data Store for storage, task queues, even cron jobs. But there are limitations, right? You have one master application running in production per project. Multiple applications will incur overhead, but you can only have one of them running at some time, but you could have different versions, of course. And there is no access to the local file system, so you have to think a little bit differently. You're going to be using external services to store state, for example. Now we get into 12-factor support. So if you go to 12factor.net, this is basically a methodology on how developers they design modern-based web applications. So there's a number of best practices built in there, and now we're going to go ahead and map what functions and services we have that map to that 12-factor design. So the first one is a single code base tracking and version control. So this allows you to do multiple and many different deployments. We have a number of things offering for this. One, you can develop inside of Google Cloud Shell. This is a microservice or a micro virtual machine. You get 5 gigs of storage. It's automatically patched and updated. It's a Bastion host and has all the API privileges to call any of the APIs within the Google Cloud infrastructure. It's hidden and authenticated using Google Authentication, and it includes all of the API and developer tools, which are consistently updated by us. So you get this great development platform immediately. Now, of course, you want to store your source code that you develop somewhere, and we have something called Cloud Source Repositories. It does integrate with GitHub, and it is like a private version of GitHub just for your project. Now, what about strictly separating build and run stages? So here we want to isolate different versions of code. Well, Google App Engine works very well for this. You can build all of your applications in Cloud Shell or on your desktop. You can upload directly to Google App Engine. In fact, we have all of the native functions. If you want to simulate a data store and other task queues and different functions, you can simulate those on your laptop. And then, of course, if they work locally when you do your unit integration testing, you can push those directly to App Engine. Keep it as a, either a production module or even as a test dev. Now, what about keeping development, staging, and production templates as similar as possible? This is where we have automation, right? So at some point, you may have a manual process to step through your deployment, but in this case, that's why we're learning Deployment Manager. If you want to automate this, we can deploy everything utilizing templates inside of Deployment Manager, which will ensure a consistent build process and allows you for many frequent deployments as well. So moving forward, well, if we want to explicitly declare and isolate dependencies, well, this is where we can create custom images. You can have your own separate source code repositories with different version controls, but now we can also have separate compute images. So if we have certain versions of code and you want everything deployed with this standard set of libraries and applications, you can create custom images which can be stored in your own source repository for that as well. Now, storing configuration in the environment. This is what makes microservices more difficult if you try to create it in your own environment, because you may have external dependencies. You don't necessarily want to publish to GitHub your private SQL database password or other passwords, and that's happened where people have found that and then it's exploited. So what you do is you store this configuration environment, what's dynamic to the VM upon boot up, in the metadata server, which can be called externally, or say in Google Cloud Storage. So we use startup scripts to pull a lot of the dynamic attributes, where your function code says, look, this is all I know how to do, but I may need to know about my environment, my external IPs, and some authentication tokens and mechanisms to allow me to communicate with those services. Well, again, you don't want to publish those with the code itself, and we can externalize those separately. What about maximizing robustness with fast startup and graceful shutdown? A number of ways to tackle this. Instant templates allow us to create the same instances every time. Managed instance groups, which will allow us to dynamically scale up and down and use the same configuration, the same hardware components, startup scripts, etc. And of course, the auto scaling, which I've just mentioned. So now we have the ability to grow our environment dynamically utilizing pre-configured templates. So when you're storing the state in the environment, you have to really think about this. Storing it in the metadata is always going to be localized, but what if you store it on local hardware? Well, if you stored it in SSD, maybe you have a megabyte of state information, whether it be object data, temp data, cache data, etc., you're going to get very low latency, and that's fantastic. But as you scale, that may not be applicable because you might have concerns with distributing your state. What if your state's local? You could probably write to local SSD every time, but maybe you want to store it in the network. Now, what if you store it on Google Cloud Storage or an NFS mount and you have a single core machine, which will actually limit you to a maximum of about 2 gigs worth of throughput? That could dynamically increase your latency dramatically. So you have to understand when you start to think about scale and you think, oh, I'll just offload the state. That's good. That's part of the design process. But understand the ramifications. How dependent were you on those performance? So measure your service level indicators of state as you start to change where that state is stored. And that is something to be key when we think about our process design. So here when we're mapping compute needs to platform products, in this case, our business logic is the application. It's going to use CPU. So where does it get these compute resources from? Well, you can use CPU on a virtual machine. You can run in containers on Container Engine or even App Engine. So what we like to recommend is when you're thinking of which platform service can offer exactly what my service needs, think about App Engine first because it's the quickest to deployment. I mean, there are companies who have already set the ground like Snapchat. They've built billion-dollar businesses exclusively on App Engine. It gets you the ability to get up and running very, very quickly. You're not going to have to tune the environment. You just have to understand the ramifications of it. If that doesn't work and you need more knobs and switches, you can certainly go down to containerization, which we also have that ability now for App Engine, and of course, straight up compute for very unique one-off use cases. So the reason why we like Google App Engine is because it's code first, and that's really what you're going to be doing. Once you've designed an infrastructure, it's all about deploying your applications. Now, if you're not writing your own and you have to go with third party, well, sure, you're going to go with VMs, and there's a different architectural design for that. But it allows you to focus on your programming, minimizing your work overhead. Also gives you dynamic scale and reliability. It's all in the platform. I mean, this is like Prego. If you remember the spaghetti sauce, it's in there. It allows you to auto scale, have different versions, do A/B testing and continuous deployment, and also canary deployments, in which you can literally turn a dial, control how much bandwidth is sent to you, various versions of applications. And again, we now support containers inside of Google App Engine. We now call it Google App Engine Flex, which gives you more flexibility, more time to run your processes before they're killed. Our standard App Engine would kill an HTTP session after 60 seconds. Now you can run it up to, I believe, even 1 hour. So a lot of flexibility there. At least look at that in your design and process before you start just saying, hey, I'm familiar with hardware, let's go that old virtual machine route. Now, next in the line comes Google Kubernetes. The nice thing here is there is a complete platform independence. You can pick up containers and run these in any other cloud provider. If you're running an App Engine, you're most likely going to be running using our APIs and all of our tools, etc. So that does lock you in a bit, but it gives you that flexibility. There is a partner called AppScale, which has created a clone of App Engine, and they allow you additional things like running in China. We don't have that service there, but you can use a lot of our same code base there because they have created these clones that use Cassandra, etc. as the backend. So look at AppScale for those situations. But Google Container Engine is a nice happy medium. There's no operating system dependencies. You're still deploying code and dependencies. And if you're already using Kubernetes on site, this allows you to simply scale, and we will manage this for you. So containerized applications will give you the flexibility to run in Google. It runs better in Google, but also as with other cloud providers. Then as a last resort, that's when you go into Compute Engine. When you need the utmost in processing efficiency, perhaps you're running HPC, you need to choose the exact hardware platform, instruction set, etc. You have a strong dependency on the specific operating system version. Perhaps you need direct hardware access. You need local SSDs, GPUs, specific drivers, and hardware performance has to be tuned and optimized. That's what it's there for. It's usually a one-off case for most applications, but there are situations where it's very clear and that's necessary. So that's why we do have that as an offering. So what about compute system provisioning? So now we're going to provision. We have to decide how the system is going to acquire new resources and adapt to changing requirements. Remember, App Engine is an auto-scaling platform. Container Engine also auto-scales, but based on containers and pods within the cluster. But in this case, we're going to cover Compute Engine and VMs. How do we auto-scale in that where it's not automagic? We have to do a little bit more configurations. So let's think about this. We have our initial thumbnail service. As it grows and needs more resources, we could scale vertically, right? We started out, say, with a 2-core machine. Google lets you go up to 64 cores, and we are working on future developments greater than that. So we could buy ourselves a lot of time, keep it simple, one single box. But remember, if it's growing that in size, that means the impact of an outage is going to be a lot more significant. So you might want to start thinking early about horizontal scaling. If you have the luxury to think early, this is the plan. I mean, sometimes you go into an environment and you have to deal with what they give you. But ideally, this is the ideal scenario. Horizontal scaling solves so many issues, but you have to do it early. You have to design ahead of time for this kind of flexibility. But horizontal scaling, it does have issues, but it has a lot of great answers. It makes automation easy because now you can do rolling deployments. You don't have to take everything offline. If you have one box, you're taking an outage. You ever been to your bank and they're still saying, hey, sorry, we're closed, or actually, they're closed at night, but their website's down. Like, really? Because they're doing maintenance. They haven't figured out how to kind of do everything in a rolling fashion, or everything's on that single database server and it has to be shut down for maintenance, etc. The problem is with the horizontal scaling, end-to-end latencies are going to increase. You are going to have a lot more network chatter. There's a different design process, but Will that really matter when it comes to scale? Because oftentimes you can't solve it. You cannot just go out and buy a bigger box for everything. Again, there's additional overhead, more network, more chatter, but again, will that make a difference with the benefits of being able to do scaling, being able to isolate upgrades, configuration? There's just so much that comes with divvying everything up into parts, right? So that's why they came up, or the Muppets always said, right? 2 heads are better than 1. Well, okay, let's go into some detail about horizontal scale. Does horizontal scale just mean 2 boxes? Well, really, we recommend n plus 3, or n divided by 3, because, for example, in this case here, if you have 2 machines, you do have fault tolerance. If one machine fails, well, then the other one has to take 100% of the workload. N to 3 allows you to maintain a pretty decent minimum without wasting too many resources, and so this way you're expecting to have some kind of failure. So the goal is just to prefer small stateless servers. Now, how small is small? And that will be something we actually start to think about when we get in through our budgeting. We may decide that we can get more efficiency with slightly larger machines, but when you're getting into the hundreds, a quad core versus a dual core could make a significant difference. So let's talk about trade-offs. We're going to balance latency, capacity, scaling, and cost. So if we start with small stateless servers and we need to increase reliability and scalability, we're going to divide into parts. That makes it simple, right? But we do have to duplicate. So we may have to have extras. We have to worry about coordination. And then, of course, creating that separation and isolation. Where a large stateful server, it's easier. It's all one big box. It's simple. We can consolidate everything on one machine. It might even make automated deployments easy. It's all getting pushed to one device. Coalescing and collocating all the data, well, it's all going to be local. So we may not have to worry about segregating different sources and getting data out of order. So how are you going to achieve your balance of design? You have to ask questions. So what are our SLOs? What do our users really care about? How do we optimize? What is the optimal size of number and parts? Do we need 1,000 microservices? What about 100? That's maybe 10x larger in scale. Maybe, you know what? Sometimes central control is necessary. Perhaps you can't get around the banking industry without taking all that database down. Perhaps you don't want eventual consistency. Probably don't, right? You need to be able to plan on adjusting. Just understand that as you grow, keep monitoring your service level indicators. Not everything in our design is linear in scale. At some point, there are potential bottlenecks that we may not know about that exist in the cloud, which is why you should benchmark and test your scale. Come up with estimates as to where they might start to occur, whether they occur inside of the actual application design or perhaps the infrastructure itself. So that's why we say design first and dimension later. So trying to dimension the solution before the design's completed and before it's iterated can really lead to confusion. So start simple, right? Don't start with, whoa, wait a minute, I can't even touch this until I understand what the network's going to look like. How many queries? Well, what kind of memory do we want, right? Do we need high-speed memory? What about local SSD? What kind of caching and storage? Do we want persistent disk? Well, we want persistent hard drives or SSD. How big? Well, all of this can be dynamically changed later. That's the cool thing about the cloud. You can switch and delete a virtual machine and switch out all of its underlying hardware. The data can easily be saved, etc. These are important questions as you start to scale, but just do a general guideline and understand the attributes of your business logic, which we're going to cover in the photo application. That will help you make a pretty good guess as to what hardware is necessary, and then you can start to tune and optimize that later.
This module covered the business logic layer. It described platform support for processing business logic, including microservices support such as cloud functions. And it provided some basic guidance to help match processing requirements with platform services. In some cases, the business logic processing needs can be supported by multiple platform services, and the choice of service will depend on the options you want in the design for its software development and administration of the system.